Hello folks, in this lesson we're going to be studying a few different things. Bond position in alkenes will be how we open this up. And then I'll show you a quick video from the Fuse School about functional groups, and then we'll do our own little study about functional groups. Today, only halides and alcohols. The bookwork that I want you to do is listed here. Just copy down these questions right there so that you have them ready for class. And the aim today is what are functional groups, so definitely copy that down. And there's a quiz associated with this lesson, so make sure you are prepared for the last few days of material. All right, first up is bond position in alkenes. Firstly, we can name this molecule to the left. This has 2 carbons and it has a double bond. So we know because of the double bond that the molecule's name is going to end in -ene, and because of the 2 carbons, we know that it will begin with eth. And in this particular case, we do not need to be specific about the position of the double bond. The reason is because there is only one position that the double bond could actually be in. It has to be between these 2 carbons, and there are only 2 carbons. So we would say no, it's in its only position. But the next question asks, do we need to be specific about the position of the double bond in this alkene? And I would argue yes, in this case we do. So the double bond could be here, but it could also be here or here. Now I do have one note, which is if I put the double bond here or if I put it here, those are actually the same location. It would just be that the molecule would be flipped. So if you think of the molecule like this, and then you flipped it around and looked at it from the back side, you would see the double bond either here or it would switch to the other side if you turned it around. So I guess what I'm saying is this is a possible location in the middle or on the end, but there's no left and right because the molecule can turn around. And so I said yes, because there are 2 possible locations for the double bond. So we still need to know how to name this guy, even if there are 2 possible locations for the double bond. If I just said, well, it's an alkene, and it has 4 carbons, so we'll use the prefix but. If I just said butene, it wouldn't be specific enough for most people's tastes. And the reason is because you could have butene with the double bond in between the 2 middle carbons, but you could also have butene where the double bond is between the end carbons. So we need to have a way of saying where the double bond is. So I recommend a method that's sort of like counting carbons, except it's going to be counting bonds. So this is bond 1, and that's bond 2, and that's bond 3. You can count from both directions, but it would still be bond 2 if you came from the right. And the double bond is definitely on bond 2 in both cases, so we're going to call that 2-butene. So we have said that you count the bonds to name it, and the name is 2-butene, so we did this and this. And now we need to name the alkene to the left. Now I'm going to give you the most popular wrong answer first. A lot of people, when they just hear about this rule, will number the bonds as either a 1 and a 2 or a 1 and a 2. And people usually will choose the 1 because it's the smallest number, and that's not what's wrong about this. And then they'll say, okay, it's 1 propene, prop for the 3 carbons and ene for the double bond. So in a lot of ways, this name is right, but there is something that I would remove. And what I would take out of this name is the 1, and I would have no number at all. And I would just say propene. Now the reason for that is because when you think about where this double bond is, it could either be here or here. But remember what I said about flipping the molecule around? If you took this molecule and you flipped it and looked at it from the other side, the double bond would be here. But that doesn't mean that the molecule changed, it just means that you're looking at it from the other side. And what I would suggest is there's really only one location for this double bond in the end, because it has to be on the end, and whether you look at it from the front or the back shouldn't change the name. So let's just go with propene as our final answer.
In this introduction to organic chemistry, you will learn the definition of a hydrocarbon and how functional groups give molecules similar properties. Organic chemistry is the study of carbon compounds. There are many. In this introduction to organic chemistry, you will learn the definition of a hydrocarbon and how functional groups give molecules similar properties. Organic chemistry is the study of carbon compounds. There are many millions of organic compounds that you can make using hydrogen and carbon and arranging them in different ways. Hydrocarbons are defined as compounds made of hydrogen and carbon only. The simplest hydrocarbon is methane. It consists of one carbon with 4 covalent bonds to hydrogen atoms. The next in the series has 2 carbon atoms, and this is called ethane, and is followed by propane and then butane, these being the names of the first 4 in the series of molecules called the alkanes. Pause this video now and try to draw the structure of hexane. Hexane has 6 carbon atoms. Here is the structure of hexane. Compare it to the structure you drew. Did you get it right? The next series is called the alkenes. These are hydrocarbons that contain a double covalent bond between 2 carbon atoms in the molecule. Just like the alkanes, each carbon atom still needs 4 bonds, but has 2 bonds already due to the double covalent bond with the other carbon atoms. The ethene molecule is completed by 2 more bonds with 2 hydrogen atoms for each of the carbon atoms. These also follow a pattern, and the next molecule in the series is propene and then butene. Pause this video now and try to draw the structure of hexene. As before, hexene has 6 carbon atoms. Here is the structure of hexene. This time there is a double bond because it's an alkene. The video tutorial on the alkanes and alkenes will give you more in-depth knowledge on the bonding and structure of these series of molecules. As we have already discussed, hydrocarbons are molecules containing only carbon and hydrogen atoms. However, the study of organic chemistry includes any molecule with a carbon backbone. Functional groups are groups of atoms which give molecules similar properties. There are many different functional groups. You may have heard of the alcohol group. This is a hydroxyl group and is a hydrogen bonded to an oxygen, which is then covalently bonded to the rest of the molecule. This group can be attached to any of the alkanes to form alcohols, their name all ending in -ol. For example, methanol, ethanol, and propanol. Pause this video now and try to work out the name of this molecule. There are 4 carbon atoms in this molecule with an alcohol group, and so its name is butanol. The alcohol functional group means that all these compounds will react in a similar way and will have similar properties. Carboxylic acids are another example of a functional group. This is the functional group for a carboxylic acid and gives an organic molecule the name oic acid. Methanoic acid, ethanoic acid, propanoic acid, and butanoic acid. There are lots more functional groups. Esters, which give molecules a sweet smell and make them useful for perfumes and flavourings. Ketones, which make molecules useful as solvents. Amines, which can be used as dyes and useful in making medicines. Some molecules have more than one functional group and give molecules different properties still. Now, by the end of this video, you should know that organic chemistry is the study of carbon-based molecules, and that hydrocarbons are molecules containing hydrogen and carbon only. You should also know that functional groups are groups of atoms which give molecules similar properties.
So you just learned that a functional group is a group of atoms that give molecules similar properties. And the first one we're going to study on this slide is organic halides. And I'll show you an excerpt from table R to introduce that. So this is what you'll see when you look at table R, and the organic halides are the first one listed. They have attachments such as fluorine, chlorine, bromine, or iodine. So you can see that these two bromines in this molecule are going to make this molecule belong to the organic halide functional group. All right, so let me move this out of the way for the time being. And then we want to know, use table R to determine what the functional group for the molecule to the right is. Well, that's going to be organic halides or halocarbons. And I'm referring to this molecule up here for this question, and it says, do you think that this molecule behaves any differently than a standard ethane molecule? So just to refresh your memory, an ethane molecule would look like this, but it would be surrounded by only H's. And I think it's pretty safe to say that this molecule down here would behave differently, and the reason is because of the two bromines are going to impart some of the halogen group properties to the molecule. So in short, an organic halide is just a carbon backbone with some halogen attachments. And now for the hard part, how do we name these organic halides? I'm going to teach you guys how to do this a little bit more naturally, I suppose. And I will point out that we're going to look at this molecule, but we're going to take its condensed structural formula and translate it into a structural formula. It begins with a CH3, which we're going to write like this. And the next thing, I'll just cross it out just to show that I've done it. The next part coming up is a CH, so it's going to look like that. There's also a Cl attached to that C, so here's the Cl. And then there's another CH3, which is going to be this. Now they are saying that the name of this molecule is called 2-chloropropane. And I think it's pretty obvious how they got that name. The propane part comes from the 3-carbon backbone. So I'll highlight that carbon backbone with the propane. And then the chloro comes from the chlorine attachment, so I'll highlight that in red for the chlorine. And the location number 2 comes from counting the carbons. And the carbons are 1, 2, 3 if you come from the left, and 1, 2, 3 if you come from the right. It's 2 in both cases. So the blue highlight is how we get the 2. So essentially you just name the parent, add the element, the halogen element, and then you provide a location for that halogen element. So before we go to the next slide, let's name this molecule up here. So remember, we name the parent, and in this case, the parent is going to be ethane. Then we name the functional group, and in this case, it's bromine, so we'll use bromo in front of the ethane. And I'd like to add a little bit extra here, which is that there are 2 bromines, so we should put a prefix in front of the bromo to say that there are 2 of them. So I will write dibromo. And lastly, I need to locate the exact places where those bromines are bonded. So this is carbon 1 and this one's carbon 2, or if you came from the right, it would be reversed. But in either case, you have a bromine on carbon 1 and a bromine on carbon 2, no matter which way you count. So I'm going to say my final answer is 1, 2 dash dibromoethane. All right, primary alcohols. We just need to figure out how to name these alcohols and look at the functional group for alcohol as well. So let me pull up the table R. So I'm going to remove this in a second just to show you to get started. Alcohols are the second thing right under halocarbons. And the functional group is an OH, covalently bonded to the molecule. And 1-propanol is written like this. So I'll go ahead and put it in. So the CH3 we'll put first. And it's followed by a CH2. So there's my 2 hydrogens. Another CH2. And lastly, an OH. So the OH is going to have to go here. Now, I am leaving the hydrogens off of some of these stick bonds, but that's okay because the reader will know that you mean hydrogen if you leave this blank. So they're calling this guy a 1-propanol. The suffix "all" is coming from the attachment, which is the OH attachment. So I'll do some highlighting there. So the "all" comes from this. And the propan part of the name is coming from the 3-carbon backbone. And the 1 is going to be coming from the location. And the location of that hydroxyl group is on carbon number 1. So that's how we get the name 1-propanol. So let me delete table R. And we'll get down to business. So what do all the molecules above have in common? They all have a hydroxyl group. I want to point out that a hydroxyl group is different than a hydroxide ion. So this is hydroxyl, this is hydroxide. Hydroxyl groups are covalently bonded to a molecule, and hydroxide ions are ionically bonded. And this will determine how they behave when they're dissolved in water. And I just wanted to point out that a hydroxyl group, which is covalently bonded, will not dissociate from its parent molecule. And therefore, the approximate pH of an alcohol is actually 7 rather than a more basic pH. So primary alcohol has a definition, and a primary alcohol is an alcohol where the OH is bonded to a carbon, and that carbon is bonded to only one other carbon. So that's the reason why it's called a primary alcohol, is because that carbon is bonded to only one other carbon. So as an example, this OH is bonded to this carbon, and this carbon is bonded to only this carbon, so that's primary. Again, this OH is bonded to this carbon, and this carbon is only bonded to that carbon, so primary. All the alcohols on this slide are primary because of where their OHs are. All right, so to name an alcohol, we're going to follow these rules. We'll always end in OL. We'll name the parent and put it before the OL, and we'll use numbers to locate the OH. So for this molecule, it's going to be a parent of ethane, so we'll say ethanol. And we don't need to put a number with this one, and the reason for that is because it's on carbon number 1, or carbon number 2 if you're coming from the right, but if you come from the left, that's carbon 1 and that's carbon 2. Or in other words, it's always going to be on carbon 1 if you count from both sides, so we'll leave the number off. The next one we already named earlier, it's the one up here, so this one's called 1-propanol. And this one does need the number in it because the alcohol is bonded to this carbon, but it could have been bonded to that carbon, which would have been a different number. Now for this alcohol, we're going to name the parent a methyl propane. I left off the E in propane because I want to add the suffix "all", so methyl propanol. And it is on carbon 1 of the methyl propanol, and it could have been on the central carbon, so that's why I am using the number. All right, let's name these two guys. So this one right here is just going to be ethanol again. This one and this one are the same molecule. And down here at the end, we have a butane with an OL attachment. So butanol is part of the name. And the other part is just locating, because the OH could be, it is here, but it could have been here or here as well. So I will say that it's on carbon number 1, 1-butanol. Secondary and tertiary alcohols are only slightly different from primary alcohols, and they have to do with the number of carbons that the OH carbon is bonded to. So for instance, here's the OH on this carbon, and this carbon is bonded to this carbon and that carbon. So that's going to be a secondary alcohol. And at the bottom, we have some tertiaries. So here's the OH, here's the carbon it's bonded to. This carbon is bonded to 1, 2, 3 carbons. And that's why we get the tertiary description. So I put in those definitions, and now we just need to name these alcohols. Same rules as before. For this guy, we have a propane backbone, and the alcohol is on carbon number 2. So we'll say 2-propanol. For the second example, we have a 1, 2, 3, 4 carbon backbone, so butane, butanol because it has the OH, and it's on carbon number 2. For the next example, we have a 1, 2, 3, 4, 5 carbon backbone with an alcohol attached. So it's going to be a pentanol of some sort. But to add the location to that, we need to count from both sides. It's 1, 2, 3 if you count from the right, and 1, 2, 3 if you count from the left. So 3 pentanol. And for the ones at the bottom, these are a little bit harder. We name the parent, and this is a methyl propane. And there's an alcohol, so it's going to be methyl propanol. And we should locate the location of the OH, so it's on carbon number 2, whether you count from the left or the right. So 2-methylpropanol. And for this last one here, we do need to name the parent first, which is a 1, 2, 3, 4 carbon molecule, so butan is going to be part of the name. It is an alcohol, so we'll go ahead and put the OL on, but I need to locate that alcohol on carbon number 2. So we'll call this 2-butanol. So we have an alcohol on carbon number 2, and we also need to locate the methyl group. So we have a methyl group down here, which is also on carbon 2. So I'm going to call this one 2-methyl 2-butanol. All right, so we have reached our pair up. I want you guys to copy down these structural formulas, and we'll name them in class, but you need to copy down these structural formulas before you go any further. And then write down these summary questions, which we'll answer in class. I hope you learned something, and thanks for watching.